So let's now begin the section of the module that deals with large-scale fading. And at this point, it's useful for us to sort of step back for a second and take a look at our overall sort of high-level model for the radio channel. Now, if you recall, all of the small-scale fading stuff that we've been talking about has basically been dealing with this channel impulse response section of the radio channel module. So we have some linear channel response H that we convolve with the transmitted signal. This linear system response or linear channel response, as we've seen, changes with distance, or equivalently if we're dealing with transmitters or receivers or an environment that's in motion, changes with time. And so this is a linear channel response, but not really time invariant. And in our discussion of the rate of change of the radio channel, the small scale fading part of the radio channel, we've seen that the channel remains approximately stationary for typically many thousands of information symbols. And so while this channel impulse response is changing with time, we can still use regular convolution, and for the sake of a group of transmitted symbols, as long as it's not too long, we can assume that the channel is stationary. And so that was the small scale fading part. So large scale fading, which is what we're going to talk about now, deals with the average received power of the wireless signal. And it's basically captured in two factors. The first one being, or two factors or two processes, the first one being path loss and the second one being shadowing. And again, we could sort of go back to our diagram and see how these two factors are represented. So the path loss component we're representing as a power gain A. So we take the square root here because our transmitted signal X is a voltage signal. And the shadowing process is represented by a second factor, gamma. And again, it's a power gain, and so we take the square root of it here. And you'll notice that both path loss and shadowing are a function of distance. And basically, these two factors represent how the average received power changes as a function of distance. As we're going to see, path loss is a deterministic component. It's basically the deterministic decay of received power as you increase the separation between the transmitter and the receiver. And shadowing is a random component and represents sort of very slow variations in average received power due to large obstacles between the transmitter and receiver, things like trees or large buildings or cars. Now, it's important at this point to define specifically what we mean by average received power. We've seen that received power can fluctuate a great deal due to small-scale fading, Rayleigh fading or Rician fading. And generally, when we talk about average received power, we're talking about the received power after you average out all fluctuations due to small-scale fading. How do you do this? Well, normally you do this by measuring the received power of the wireless signal at several different points in a small localized area. And so we've seen that you can get statistically independent or different small-scale fading values after moving by as short a distance as a few centimeters in some cases, depending on the wavelength of the wireless signal. And so typically if we want to measure average received power at a particular point, we define 1 meter by 1 meter square. We take our measurement receiver, we move it around to a bunch of different locations in that 1 meter square. Each of those locations gets a different small scale fading value. Then we average all those measurements together. That essentially averages out the small scale fading, and we're left with our average received power, which is what we're talking about here. And the reason why it's important to keep, the kind of the experimental aspect of measuring average received power in mind is because, as we're going to see, both path loss and shadowing are very, very strongly based on empirical data, experimental data, more so than a theoretical model. Now, a classic example of the type of measurement result or measurement plot that we use to develop both a path loss and a shadowing module is shown in this slide. So in this slide, what we have is a series of points, or a scatter plot, where each point in the scatter plot represents a different radio channel measurement. And so what the authors of this paper would have done is basically have gone out in an outdoor environment, in this particular case, and measured average received power at a variety of positions in their outdoor environment. At each one of these measurement locations, they would have determined average received power as I described on the previous slide. Once they collected a large number of data points, as we can see here, there's a lot of points on this plot, they would then create a plot of path loss, which is just the attenuation between the transmitter and the receiver, versus a log of distance, transmitter-receiver separation in meters. And so this is essentially a log-log plot because, of course, decibels are calculated by taking the log of something. And the way that they would have determined path loss, or basically the attenuation between the transmitter and the receiver, is that they would have been transmitting at a known transmit power, and they would have captured their measurement at a certain average received power, and then just the difference between those two in dB represents the path loss. As we can see here already, after creating the plot, what the authors did is they created least best fit lines to the data using a least squares best fit, and you can see those lines represented in black. As it turns out, it is these least square lines that are going to be absolutely key for both creating a large scale channel model for creating both the attenuation part, or the path loss part of the channel model, and the shadowing part of the channel model. So I want to start by first focusing on the path loss part of the large scale fading model. And path loss determines the average received power of a radio signal as a function of distance, as a function of the distance between the transmitter and the receiver. And there are actually quite a few different equations or models for calculating path loss, many of them developed based on experimental data designed to fit a certain scenario or a certain environment. I'm just going to give you sort of the two most basic, but also probably the two most widely used equations for calculating path loss. The first equation is the Friis equation, which is used for free space, right? So you've got a point source radiator for your transmitter, a certain antenna for your receiver, floating in free space so there's no reflections. And when you have this, you end up getting your received power as a function of distance equal to the square of the wavelength of your signal divided by 4 pi times the the distance between the transmitter and the receiver. And then this factor is multiplied by the transmit power and also the gains of your transmit and receive antenna. Now, if your transmit and receive antennas are they radiate perfectly in all directions, then they both have a gain of 1. If you're dealing with a directional antenna, then typically you'll have some directions where you'll have a gain of greater than 1, and then you'll have some other directions where your gain will be less than 1. And this equation, like I was saying, it can be used for free space, which is kind of an artificial situation, but it can also be used to calculate path loss for very small separations between transmitters and receivers. So if your two antennas are separated only by a meter or 2 meters and they're very close to each other, there's no obstacles between them or really close by around them, then this equation is reasonably accurate. The second, more generally used equation is what is commonly called the path loss equation, and is typically expressed in dB. So here we have the received power of our signal in dB, again as a function of the distance between our transmitter and our receiver, equal to a reference received power, P naught, at some reference distance D naught. Now, this reference distance is usually fairly close to the antenna, far enough away that you're in the far field of the antenna, but still very close so that there's not any obstacles between the transmitter and the receiver. And so D naught is typically chosen as a meter or 2 meters. And if you want to calculate P naught at this separation of 2 meters, let's say, what you use is the Friis equation. And so the Friis equation is used to calculate this reference distance at D naught. And once you have that, you see we've got a second factor down here, which is the log of the ratio of the actual separation between the transmitter and the receiver, D, divided by D naught, multiplied by 10 times n, where n is something called the path loss exponent. And to understand the path loss exponent, we need to go back to the log-log plots, the log-log experimental plots of attenuation versus distance. So if we think about our path loss equation and that path loss exponent n, since it's multiplying the term that decreases the average received power, obviously the bigger n is, the more rapidly received power decays with distance. And so it turns out that n is not a single fixed value for all cases, but varies with environment. And generally speaking, the more clutter there is in an environment, or the more crowded it is with reflecting objects, the larger n is going to be. And so if you are in a rural environment with not very many trees or obstacles between the transmitter and the receiver, or perhaps in a very short range indoor environment where you've got a good line of sight path between the transmitter and the receiver, n is going to be fairly low, probably close to 2. However, if you are in a very cluttered environment, let's say you're in a dense urban environment in the downtown core of a city with lots of large buildings between the transmitter and the receiver, n is going to be bigger. And this should match our intuition, because the more obstacles there are between the transmitter and the receiver, the more quickly we would expect average received power to decay with distance. And so that's kind of an intuitive feeling as to where these n values are coming from, but you could also ask the question, okay, specifically, how do we actually calculate these values? It turns out that we need to go back to our experimental plot. The value of n ends up being the slope of the best fit line to our path loss versus the log of distance scatterplot measurements. And so here we have two sets of measurements, again from the paper I referenced a few slides ago. The blue dots are from one set of measurements from one environment. The red dots are from a slightly different environment. And so if we look at the blue dots first, and the blue dots, as is indicated in the legend, or represent line of sight data, or data collected where there was a clear path between the transmitter and the receiver. We can see that there are random variations around the best fit line, but if you look at the slope of the best fit line, the slope is approximately equal to 2. And so for that line of sight environment, we would say that the path loss exponent n is equal to 2, because n is the slope of the best fit line to this data. In the non-line of sight situation, where we have the red dots on the scatter plot, we can see that the slope of the line increases to 3. And again, this matches sort of the intuitive explanation I gave a few minutes ago. In an environment where there's lots of clutter, where there's not a clear path between the transmitter and the receiver, we get a larger amount of attenuation. The average received power is going to decay or drop off much more quickly with the distance, and that's represented by a larger path loss exponent. And sure enough, we see that exact effect on this plot. So as we increase distance, if we go from 10 meters to 100 meters, we can see for the red data the attenuation gets much higher, much more quickly than it does for the blue data. As a result, we have a larger path loss exponent. The slope of the best fit line is equal to 3 in this case. And so generally, people will use kind of rules of thumb for path loss exponents. 3 is a typically used number for indoor environments. 4 is a typically used number for sort of the dense urban area of cities in an outdoor environment. And we tend to round these path loss exponent numbers to integers, but it's important to point out that path loss does not necessarily have to be an integer quantity. Again, it's just the slope of these empirical lines, and so path loss could really be sort of any kind of a fractional number. Okay, so if the path loss equation was the only way to represent the average received power of a wireless signal, if we created a scatter plot of the values that we calculate using the path loss equation, then they would all fall on that best fit line. However, if you recall, there was quite a bit of variation around that best fit line, and that sort of random variation is what's represented by the shadowing factor, which is the second large-scale attenuation factor. Shadowing is a multiplicative factor that accounts for large obstacles between the transmitter and the receiver. So things like big houses coming in to obscure the line of sight path between the transmitter and the receiver, large vehicles, stuff like that. And when working in decibels, shadowing, because it's a multiplicative factor in the linear domain, when working in dB, shadowing becomes additive. And we basically just tack the shadowing factor sort of on the end of the path loss equation right here. The distribution of the shadowing factor gamma is determined experimentally or empirically from the average received power measurement plot. And so how do we determine the distribution of that shadowing factor? Well, the first thing we do, and this is something we had to do to determine the path loss exponent, the first thing we do is we create the best fit least squares line to the data, right? And that's represented by these black lines. Once we have the best fit line to the data, the shadowing is basically just the distribution of the data points around that line. Remember, the whole purpose of the shadowing factor is to account for the fact that average received power just doesn't lie on a nice flat line, but there is some random variation around it. And so basically for each of the data points, what we do is we measure how far each data point is from the line. And so I'll try and draw it in here. We could measure the variation for that point. We can measure the variation for that point. We can measure the variation for that point. And we essentially take this difference value, how far each point is from the best fit line, and we determine a histogram or a PDF for that line, or for all of those values. And what we find is that when we're working in the decibel domain, when we're working in the log domain, we find that the shadowing factor is normally distributed or Gaussian distributed in dB. And so when you convert that back to the linear domain, it's the shadowing distribution follows the log normal distribution. And that log normal distribution holds for pretty well every environment. There's been a lot of shadowing studies done both for indoors and outdoors, and this log normal distribution, or if you like, the Gaussian or the normal distribution in the log, or when you're working in DB, seems to hold pretty much across the board. One last important thing to note, though, about the shadowing distribution is that while the Gaussian shape, or the log normal shape, tends to hold both for indoors and outdoors, the standard deviation of the shadowing variations will change depending on environment. So when you're dealing in the and this variation is typically expressed in terms of standard deviation while working in the log domain. And so if we're doing, or if we're looking at shadowing in an outdoor environment, we generally see variation with a standard deviation kind of on the order of 8 dB or so. 8 dB is a fairly commonly used number. Whereas if you are indoors, the standard deviation of your shadowing tends to be closer to 1.5 or 2 dB. So again, the Gaussian shape is the same across environments when working in DB, but it's just that standard deviation that's going to change. The last thing that we can talk about, or that we should talk about with shadowing, is its rate of change. Now, shadowing tends to change on a much slower time scale than small scale fading. So in many ways, the shadowing factor and the small scale fading factor are quite similar, right? They're random factors or random parameters that cause fluctuation in the received power of the wireless signal. However, shadowing changes much more slowly than small scale fading, and when we think about this for a few minutes, this should make sense. So recall, small scale fading is caused by the constructive and destructive interference of the radio waves arriving at the receiver. And so it makes sense that sort of the distance scale over which we experience different small scale fading values should kind of be on the order of the wavelength of the wireless signal, because it's the interference of these waves that are causing the small scale fading variation. Now, remember, shadowing represents random variation in received power due to large objects kind of coming between the transmitter and the receiver. And so if we think of a large object kind of as a house, then we really need to travel kind of the width of a house, right? So tens of meters before we experience a significantly different random shadowing factor. And so small scale fading will vary sort of on the order of centimeters. You move centimeters and you start to see small scale fading variation. With shadowing, you tend to need to move many meters, several meters. Shadowing is just a stochastic process, right? So it's a random factor that changes with distance, or equivalently with time. And the autocorrelation of shadowing, when you express it in terms of distance, has been shown to follow an exponentially decaying model, and that's the equation I've given here. And this exponentially decaying autocorrelation for shadowing holds pretty well both for indoor environments and outdoor environments. And as we were saying, the correlation distance will be tens of meters outdoors, because it's kind of shadowing is sort of caused by large buildings. Indoors, the correlation distance is quite a bit smaller. It tends to be on the order of 1 or 2 meters, because the obstacles indoors are things like large filing cabinets or room dividers or doors and things like that. But again, even at a distance of 1 or 2 meters, this is still quite a bit slower than small scale fading, which tends to vary on the order of centimeters.